Student, today we are again back with polymers. In our second phase, we have the preparation of polymers. In the preparation of polymers, we would rather break up into two parts. One is about the preparation of addition polymers, and number two, that is the preparation of condensation polymers. So let us focus now more to addition polymers, how they are formed or how they are being prepared. So student, I have made out a chart for you. Addition polymers, they can be of three types. One is free radical polymerization, number two cationic polymerization, and number three anionic polymerization. I repeat once more: free radical polymerization, cationic polymerization, and anionic polymerization. Though this cationic and anionic part is not there in your scope in the syllabus for class 12. So what we are going to focus is on the free radical polymerization. In the free radical polymerization, you have again break up into three steps. Number one, it is chain initiation. So it will start the chain. So chain initiation process, number one. Number two, chain propagation. So it will just go on propagating one monomer linking with another monomer to form a large polymer. And finally, it ends up with the chain termination. So I repeat once more, for the free radical transmission or free radical polymerization, you have chain initiation, chain propagation, and chain termination. Our work is to see on examples that include number one, polythene, number two, polypropylene, which we call it as Harpulon, PVC, polyvinyl chlorides, Teflon, that is polytetrafluoroethene, polystyrene, that is called Styrene, and here we have Polyacrylonitrile or Orlon. So these 6, 1, 2, 3, 4, 5 and 6. Here we divide polythene again in two categories. One is LDP and other is HDP. LDP means low density polythene. They have low melting point. They are flexible. They should be flexible. Sometimes you have seen some of the polythenes which are very flexible. You can make squeezing toys and all. Squeezing, like tomato sauce we have in the pouch. So these type of things we go for making through LDP. And HDP means high density polythene. They have high melting point, and they are used for making those type of polythenes which are very hard, like making dustbins, for making chairs, for making water buckets, mugs. So in this case we use the high density polythene. What is the main difference between the two is we take here ethene or ethylene, whatever you say, the same ethene here and here you can see the same thing. A temperature of 350 to 570 Kelvin is being given in the presence of oxygen. At a very high pressure, 1000 to 2000 atm pressure is a very high. 1000 to 2000 atm pressure, we get this polythene. But this is a big thing, that polythene, it is branched polythene. And due to this branched polythene, what happens is, this polythene, due to the multiple branch on both the sides, they cannot be folded. And if they cannot be folded, they would have a low density in this case. And here we use, as I told you, we are making the squeegee toys and all with this type of polythenes. And remember here, we have to give a temperature between 350 to 570 Kelvin in the presence of oxygen. So oxygen flow should be important. And next point is about the pressure, a huge pressure. That is uncountable pressure. We require here 1000 to 2000 atmospheric pressure where we make this polythene. And remember, this polythene should be branched, and if it is branched you cannot fold it. Sometimes I have shown you before, if this is a polythene, if I can fold it back, then the density increases. But if I cannot fold it, if I have this one, I cannot fold it back, that indicates the density would be low. So in the branched polythene, when it is branched polythene, the density is low, and when it is a linear polythene, you can fold one after another, forming a multiple layer, and in this case you get a high density polythene. In making high density polythene, you require a temperature lower than the before, 333 Kelvin, 6 to 7 atmospheric pressure, and catalyst what we are going to use is Ziegler-Natta catalyst. Remember, this is very important, Ziegler-Natta catalyst, and we have to use this one in making a linear polythene. And this linear polythene, usually they are high density and they have a high melting point. Our next category is about the propylene. It is also called as Harculon. This is very interesting, like student, this is 1-propene. This is 1-propene, P-R-O-P-E-N-E, propene. And this 1-propene, in the presence of triethyl aluminum or titanium tetrachloride, not or and, this should be plus. If you add here triethyl aluminum and titanium tetrachloride around 20, at room temperature 293 to 393 also it can work. So when we give here, we are getting here propylene, it goes on branching n number of times. So this type of compound is called propylene or Harculon, and you can know it is very stiff, it is hard, it is thermoplastic. That means if you heat for long, if you heat at a high temperature, you can mold it to some other different shape because it is thermoplastic. They are good moisture resistance. So as it is a moisture resistant, you can use for making raincoats because it will not allow the water to percolate inside. It is a good resilience. Resilience means if you give a pressure, it changes the shape. Again, when you decrease the pressure, it comes back to the original shape. So we can use it for making the squeegee toy. Here, good resilience. I repeat once more, by applying pressure they get deformed. On the releasing out the pressure, they come back to the original shape and size. And so it is used as a good resilience, and that is the squeegee toy we use here. In packing the films, sometimes you have seen some bubbles type materials we are using for packing the material. So those fragile materials which we are packing it up usually is made up of this propylene. It is also called as Harculon, and this is very important in making the packaging materials. Next thing is about the PVC, the PVC board, PVC pipes, even this pen, just check it here, this is PVC, polyvinyl chloride. So this is polyvinyl chloride, CH2CHCl, this goes on repeating. You can see these are the chain initiation and for the progression. So it will join for n number of such kind of monomers to make a polymer. And here you can see we have taken ethine, CH triple bond CH, in the presence of HCl, and with the salt of any kind of mercury. Here it produces CH2 double bond CHCl. So this is vinyl chloride. So vinyl chloride, if you take n number of vinyl chloride in the presence of organic peroxides, this is very important again. What the catalyst we use is organic peroxides, and at a pressure, very high pressure, around some 500 to 1000 atmospheric pressure. Here it was quite high. You need not to produce that very high pressure. 500 to 1000 atmospheric pressure will work, and it is going to produce CH2CHCl, the n times n. So I have shown you how you are going to make vinyl chloride, and from vinyl chloride, by the presence of organic peroxides and high pressure, you are going to create this polyvinyl chloride. And polyvinyl chloride, like it is used for electrical insulations. Like PVC boards, this PVC boards is insulator. PVC boards are insulator. It will not allow the electricity to pass through it. So it is used in making the boards, switch boards and all. It is used in making piles, plastic dolls, which cannot be deformed easily. Vinyl floorings, you can see anti-rust floorings. anti-hydrate floorings. So there in these cases, the floor walls, the mat walls are usually thin film of this PVC are being smeared over so that they give a resistance to water. Our next one is about the Teflon. It is called as polytetrafluoroethene. Polytetrafluoroethene. That means it's number of times, n number of times, tetrafluoro. 2 fluorine here, 2 fluorine here. So tetrafluoro and it is ethene. So it is poly times tetrafluoroethene. So you can see here, students, if you take this for n number of times, it gives you CF2 single bond, because this is, remember, this is a sigma bond and this is the pi bond. The pi bond under pressure and temperature, it breaks open and the bond is formed between this carbon and that carbon, and they are initiating the chain of these monomers to make a polymer. And what it is used for, non-stick coating on the cooking utensils. I have told you before that like this cooking frying pans and all, we use a Teflon coating. During these days, I used to see some advertisements saying that if you use Nerolac or Berger or Asian Paints, whatever it is, there is a Teflon coating. If you put your feet or some dust being smeared on the walls, you can easily rub it off, because it does not percolate any kind of dyes, it does not percolate any kind of water or anything else. Students, you have seen the inner lining of the refrigerator. Whether you have seen the outer castings of the TV box, whether you have seen about a radio or a transistor, the outer part. Yes, students, it is nothing but the polystyrene or styrene. So it is a hard covering. Even these cars, motorcycles and all nowadays, we are using a polystyrene or styrene instead of any metals. So we just say it's fiber, but actually what is that? Polystyrene or styrene. So it's a hard covering. You can see the interior of your car. You are taking the box and all, everything is polystyrene. The outer caskets or the gaskets of the TV, radio, transistors and so on are all this polystyrene. Refrigerator lining, toys, TV bodies, hot drinking cups. Yes, nowadays you have the cups. These are, you say, fiber cups, but it does not melt even you put hot water or hot milk or hot tea. It doesn't melt. Why? Because of this polystyrene. This is actually styrene. This is styrene, a benzene added with ethene. When a benzene is added with ethene, it is called styrene. See the spelling? Styrene, S-T-Y-R-E-N-E, styrene. And when this styrene you multiply it for n number of times, when you multiply it for n number of times, it is called polystyrene, and it is used for the refrigerator lining, toys, TV bodies and hot drinking cups. This is a monomer, and this monomer you just go on multiply until unless you get your desired polymer. Now we are at the last part of the preparation of addition polymerization, the last part, and here we go with the PAN, polyacrylonitrile. In short form we call it as Orlon or acrylon. Students, you have seen now that we are using sweaters or synthetic carpets. All these are made with Orlon. You have seen, students, that to get the wool for a sweater, you have to take 5 to 6 sheeps. Those sheep you have to drag out, you have to shear out the wool to make a sweater, 5 to 6. But it should be very costly. It should not be less than 5,000 for making a good sweater. Now come back. For common people, it is not affordable to buy a sweater which ranges above 5,000. So we go for making this with polyacrylonitrile or Orlon. This is a substitute of wool. But like when you go out wearing the sweater with the Orlon or acrylon or the PAN, polyacrylonitrile. If the light falls on the wool, it will be scintillating, it will be shining. This is all the thing that is different from the natural wool. Here we have the cyanide group attached with ethene. In the presence of peroxide, it have n number of times of this acrylan. So polyacrylan or polyacrylonitrile, or short form we call it as orlon. So it is a substitute of wool and it is used in making the synthetic carpets. So student, one more as in a summary of addition polymerization. It can be of the free radical, it can be of cationic polymerization, it can be of anionic polymerization, and we have examples on polythene, and the polythene goes with LDP, that is low density polythene, high density polythene. Our second part is the polypropylene or harculon. The third one is about the polyvinyl chloride. The fourth one is about Teflon, the polystyrene, and the acrylon. So I will just take 2 minutes time. You know how important this ethene is for addition polymerization. CH2 double bond CH2. This is what we call as ethene, E-T-H-E-N-E, ethene. Okay, so we have gone with ethene. Now when you go with CH2 double bond CH, you replace one H with Cn, it becomes acrylon, or it becomes acrylan. So this is acrylan, A-C-R-Y-L-A-N, acrylan, and you can multiply it for n number of times, so polyacrylan. Next is about CH2 double bond CH. One hand is replaced by benzene. It is called styrene, S-T-Y-R-E-N-E, styrene. Now again this is CH2 double bond CH. One hand, if you add with this CH3, as we can see here, CH2 CH CH3, this is propene, P-R-O-P-E-N-E, propene, and this propene for n number of times, if you just go on adding it, it is called polypropylene or the harculon. Here also you can see, if you take CH2 double bond CH followed by a Cl, it is called vinyl chloride, V-I-N-Y-L, vinyl chloride. And this, if you multiply it for n number of times, it is called polyvinyl chloride. So you can see how important the ethene is. Ethene to acrylan, acrylan to styrene, to propene, to vinyl chloride. So you can have this monomer, multiply it for number of times to get your desired product, and that is all. You can go with the addition polymerization in the preparation of addition polymerization. Hope you have understood this preparation. In our next episode, we will be going with the preparation of the condensation polymerization. Thank you and have a nice day.